Hello and welcome to What's Up With That, the series that demystifies all things Chrome. I'm your host, Sharon, and today we're talking about processes. There are so many process types in Chrome. How do they form the multi-process architecture? What exactly is a process? Here to answer all of that and more is today's special guest, Darin. Darin was one of the founding members of the Chrome team and pretty much did the first implementation of the multi-process architecture, so is well suited to answer all of this. Plus, created the IPC channels that Chrome started with. If you want to learn more about IPC and Mojo, check out the last episode with Daniel for lots more on that. So, hello, welcome Darin, welcome to the show. Thanks for being here.
Thank you. Great to be here.
Yeah, cool. So, first question, what is a process?
Right. So, process is the container in which applications run on your system. Every process has both its own executing set of threads, but it also has its own memory space. So that way, processes have their own independent memory, their own independent data, and their own independent execution. And the system is multitasking across all of the processes on the system.
Cool. Chrome is basically an operating system that runs on top of your operating system. So there probably are parallels between Chrome's representation of a process and the actual operating system ones. So what are the similarities and differences, and how do they interact?
Well, yeah, I mean, you can talk about a lot of different things. I mean, so Chrome is made up of multiple processes. We run different tasks in different processes. That's done for multiple reasons. One is so that they can run independently, so that there's performance benefits that come from the fact that they're running independently. Back in the day, the original idea was that it would give us, allow us to take advantage of the operating system's preemptive multitasking that it already has. And to actually allow web pages to run concurrently and to be managed just like any other concurrent task that the operating system would manage. So that's the original idea there. And in that way, this model of Chrome divided into multiple processes just allows the Chrome itself and all of the tasks that it has to really take advantage of multi-core systems, so that if you have more computing power, if you have more cores, you have more hyper-threading going on in your system, then it's possible for more things to happen concurrently. And Chrome's workload can be spread out that way because Chrome is very broken into all of these different processes and all these different threads. In that way, it's taking advantage of and mirroring the capabilities of the OS and providing that as a substrate for web and for browser and for how all these things work. How Chrome then has to be similar is that also, like an OS, Chrome has to manage all this stuff. From simple things like how much resource should a background tab be using? Should its timers be running when it's in the background? To much more complicated things when you talk about should a process stay alive or not? If you look at Chrome OS, where system resources can be so limited, it's necessary, or on mobile, necessary to terminate some of those background processes, to close some of those tabs behind the scenes, even if the application makes it look like those tabs are still open. So the level of management is a big part of, in that way, it's being kind of like an OS.
Is Chrome's representation of a process, are those generally one-to-one with a system process, depending on which system you're on, or is there an abstraction layer?
No, well, absolutely. When we talk about a process in Chrome, we mean an OS process. And so we might have multiple web pages being served by that single renderer process. We do try to spread the load across multiple processes, but we also independently decide how many processes to actually create. And it can be based on, there could be good reasons from, like I said, a performance perspective to having tabs assigned across multiple processes. But there can also be good security properties, like letting the web pages be allocated to different processes means that those web pages are not running in the same process, meaning they're not running the same address space. And from a security perspective, that has really great properties because it means if a web page is able to tickle a bug in the rendering engine in the V8 or in part of Blink, and somehow get a privilege escalation, like start to be able to do things that JavaScript normally can't do, it's still going to be limited by the capabilities of that process. and what it has access to. And so if that process has really only the data for the web page that was providing the problematic JavaScript, well, it's not really getting access to anything it didn't already have. Mm-hmm. And that's kind of the whole idea of process isolation and sandboxing. And then on top of that, you limit the capabilities of that process by really leveraging the OS process primitive and the kinds of restrictions and capabilities that can be removed from that process to achieve an isolation for web pages, for an origin, or for a set of web pages. I say set because we might not want to allocate a process for every single tab or for every single origin or for every, because that might just use up way too many system resources. So we have to be thoughtful there too.
Yeah, so this is quite closely related to site isolation, which isn't the topic of this video, maybe the next one. Mm-hmm. So terms that are used often and sometimes interchangeably are multi-process architecture and site process model. So mm-hmm. These aren't exactly the same thing, but I think, can you explain the difference between them and what each one is for? Because there are similarities, but...
Sure. I mean, I think to me, the phrase process model, it's talking about like, what does a particular process represent? What does it do? And then when you say multi-process architecture, I'm thinking of the whole thing. It's all packaged up. It's a multi-process architecture to build a browser. At the end of the day, user is hopefully not so aware of the fact that this is how it's built. Earlier on in Chrome's history, the Windows Task Manager didn't do a very good job of grouping processes by their parent. And so if you open the Task Manager at the OS level, you'd see just a spew of processes that Chrome was responsible for. And it could be a little disconcerting for people, a little tangent. But now in the more modern versions of Windows, they do kind of group it all to the parent task. And so it's a little easier and less sort of in your face that like Chrome is creating all these processes. But yeah, at the end of the day, it's just the multi-process architecture is like, that's the embodiment of the whole thing. And we have these different process types that make up that whole thing. There's the browser process, the main one. And then a renderer process is the name we give to the processes responsible for running web pages. And then we have a few other process types that are part of the puzzle. A networking process, a GPU process, a utility process, and occasionally in the lifespan of Chrome, other types of processes. We had plugin processes, for example, when we were hosting Flash in Chrome. And the native client had its own type of processes as well. So what's that all about? Really, it's... I can go into it if you want me to go into all the details there, but...
Yeah, I think we'll run through... This is a perfect segue. We'll run through each of those process types you just mentioned and mention a bit about what they do, how much privilege they have, maybe how many of them there are, because some of them, like, there's only one of. So I think it makes sense to start with the browser process, which is the process, and is often likened to the kernel in an operating system.
Yeah, so the browser process, kernel, operating system, broker, these are kind of good analogies for what the browser process's role is. So it's the application process, the main one that starts up initially, and it's the one that hosts the whole UI of the app. And it's going to spawn these child processes, the renderer processes, the GPU process, and so on to help fulfill its goals. So very early on, we started with this design where WebKit, the rendering engine we were using from Apple, it could be built as a COM control and registered on the system and loaded as a DLL. And then in order to run that in a child process, it was using HWinds and all the sort of standard Win32 isms to do its job. And we started out by just literally trying to capture a bitmap rendering of WebKit and send it over to the browser process where we could present that bitmap. Actually, rewind even further. The very first version took advantage of the fact that Windows supports having HWinds hosted in different processes and threads. And so we literally just took that HWin from WebKit in that child process and stuck it into the window hierarchy of the browser process. And we drew our browser UI around it, and WebKit was there, but it was running in a different process. And if we ever needed to tell that process to do something, we just send a WM user event post message to it. And that's like something Windows lets you do. So it felt like a very simple toy kind of way to try it all out. A lot of limitations to that design. Pretty quickly, we realized we didn't want to just be in that kind of setup, and we moved to building our own IPC channel, a pipe, so that we could communicate and really get to the point where WebKit's running there without an HWind, without its own Win32 windowing constructs, but instead it's just kind of an image generator. And we take the image that it generates, the bitmap, send it over our IPC channel to the browser process, and the browser process is where we have our window hierarchy. Browser process, we display that bitmap. Browser process is where we collect user input and send it to the pipe into the renderer, where we then feed it into WebKit. That was the original architecture of Chrome. So in that world, the browser process is your application process. It has all the UI, and it's really like this glorified image viewer. And the renderer process is literally just like it's running WebKit. Now blink. It's running the rendering engine, and it's producing those images whenever like an update occurs, a layout occurs, or some invalidation occurs. And we got a little fancy. It was producing just the sub. It would know, oh, I really only have a small damage rec, so I don't have to produce the whole image. I just produce a small part and send that over, and then we paint that into the part that the browser is retaining an old image of, and it can update just that one part. And so that's a very simple approach that we took when building this whole thing. And so those renderer processes become very much just, very simplistic in that they aren't interacting with the rest of the OS in a very deep way. They are just taking input events from this pipe and sending images back. When they need other services, like they need network access, instead of going straight to the network from the renderer process, because we started to realize, hey, we might want to sandbox and restrict those child processes. And also, we needed the notion of like cookie jar that was shared across all web pages, so that if you visit Gmail in one tab and visit Gmail in another tab, you're still logged in. We needed the network stack to be in a unified place. So it meant that not just would we send images up to the browser, but now we would send network requests to the browser, and then the browser would respond with the network data. And as a result, we started to go down this path of centralizing access to system services and resources in the browser process. It's becoming therefore like a broker to the system that the renderer now is unable to. Not unable. It's asking the browser for everything it needs. It's communicating to the browser to get access to all the different resources. And that allowed us to then restrict the renderer process considerably, so that it doesn't even have access if it wanted to touch the file system, to touch the network TCP/IP implementation or any system resources. Mm-hmm. So the sandbox really is all about like how we applied those restrictions, taking away the capabilities of a Windows process. So in the very early days, there was just browser process and renderer processes, and we would allow multiple renderer processes to be created as tabs were opened. And we put some restriction on the number of processes based on the amount of RAM that your system would have, thinking that processes maybe have some inherent overhead, which they do. Certainly there's the overhead of the V8 heap, that is allocated once per process or once per isolate, if you're familiar with the details of V8. And so we didn't want to have so much of that kind of, so we thought there was some limit to how many processes we should have. Mm-hmm. Later on, other processes types started to started to emerge. The next one that came was the plugin process. Because in order to get YouTube to work back in 2006, you needed to support Flash. Mm. And Flash has two modes. It had a windowed mode and a windowless mode. And the difference is whether it drew itself into an HWind or if it would just produce a bitmap itself. But regardless of what mode it was rendering in, it still wanted direct system access. Like it wanted to touch the file system. And so if we're going to run it in our browser, it can't run in the renderer process. It has to run somewhere else. And so, yeah, in the frenzy of like, gee, wouldn't it be nice if we could have sandboxing? It was, how the heck are we going to sandbox and isolate plugins? Because the way plugins integrated with WebKit is that WebKit just directly called into them and said, hey, if it's a windowless one, give me your bitmap. I'm going to include it in my rendering. If it's a windowless one, it also means it's dependent on WebKit to feed it events. And so, how does that work? So we ended up building a process type called the plugin process type for MP API plugins, Netscape style plugins. All stuff that doesn't exist anymore. It's wonderful. And took MP API as this interface that was once upon a time, I want to say, kind of like, my head was going to some unsavory words. It was kind of pooped out by somebody at Netscape to make Acrobat Reader work over the weekend, and then it became a stable API. And lots of regret and sadness probably followed, but as a result, things like Flash were created, and web became very interesting in some ways. Wonderful story about Flash, I think. But anyways, supporting that stuff meant dealing with some gnarly frozen APIs and figuring out how to can stitch all that together in the renderer process. So WebKit would talk to something that wasn't actually in its process, that was, or again, another IPC channel running in a whole nother process. We wanted plugins to still not run in our browser process, but to instead run in their own process, so that if they crashed, they wouldn't take down the whole browser. And Flash and other plugins were notorious for crashing. So it was a must that they run in their own process. But we figured they couldn't be sandboxed as tightly as the renderer, as WebKit, because they already were, accessing the system in very deep ways.
Mm-hmm. Cool. Lots of
more processes got added later, like the networking, the GPU process, and NACL. I can tell the story about those too if you're interested.
Oh, sure. Yeah, let's hear it.
Okay, so 2009 era, I think, maybe 2010, I don't know. Somewhere along the way, we started building Chrome for Android.
Mm-hmm, right.
And you might recall I described how the renderer was really kind of like a glorified image viewer, or the browser is sort of an image viewer, and the renderer's job was to produce a bitmap. And then we send it over to the browser would draw the bitmap. Mobile systems were not going to work very well if this is the way the drawing was going to work. If you think about how scrolling works, or worked back then, scrolling a web page back then meant telling the computer to please move all the pixels, and then to draw another bitmap where pixels are not existing yet and need to be drawn. So you do a move followed by a mem copy. And so this is how original Chrome was built. It would, if you were scrolling, it would be, we need to shift pixels, and here's the bitmap we need to stick in the part that's exposed. Do that all quickly, and do it over and over again. And that kind of operation is just not good if your goal is like nice responsive scrolling on a touchscreen. Instead, the way mobile systems were built is using GPU rendering and compositing engines powered by GPUs. So that instead you are offloading a lot of that work to the GPU. So it was necessary to restructure Chrome's rendering pipeline. For mobile at least. But because we were doing that, we could also take advantage of it on desktop. Meanwhile, we were also on desktop starting to invent things like WebGL. Initially, WebGL, the precursor to that was this plugin called O3D, which is a 3D graphics plugin using the wonderful plugin APIs that I talked about before. But it provided this way to have 3D graphic scenes and build immersive kind of 3D content. That team at some point switched their sights on how to make that a standard through WebGL. Wonderful stories around that. But it also entailed figuring out how to do OpenGL, essentially, because WebGL was just OpenGL ES, and how to do that from a renderer, from that Blink child process, how to do it there. And really that meant that, okay, this process is going to be, these sandbox renderers are going to be generating a stream of GL commands. Where do they go? What do we do with that? And also, we know that it's possible to write shaders and possible to write GPU commands that can really wreck, can cause havoc, can be problematic, can cause the system to crash your process. So we don't want that happening in the browser process, because we want the browser process to stay up so it can be that it can be the manager. So the GPU process was born. This will be the process that actually talks to the OpenGL driver or DirectX under the hood via Angle on Windows. And so now we set up another pipe from the renderer over to the GPU process, and the stream of GL commands are being sent over there. And over there, he's talking to the driver. And if you sent something bad, the driver's going to say no bueno and crash your process. And we would find that the browser would see the GPU process died, and it would maybe give you a warning or let you reload the page, and it'll try again. And so that's how we therefore were able to leverage processes to give us that isolation, but also give us that robustness, give us that capability. And that led to a lot of complexity, but also a lot of really amazing sophistication around the compositing engine. Chrome CC library was born subsequently, and all these things that have led to the modern way that we render the web on Chrome now. Skia learned how to render to OpenGL, etc. And GPU process. Next one came along was the network process, which was really born out of the idea of, gee, wouldn't it be nice to isolate the networking code into its own process that could be more tightly sandboxed, because the networking stack tends to be a surface area that's accessible by attackers. Just like the V8 and JavaScript engine is parsing lots of stuff and very exposed to attack surface from would-be attackers, the network stack, same thing. You've got HTTP parsing and various kinds of other kinds of processing happening very close to content that attackers can control. And so this project, rather elaborate project to move the networking stack out of the browser process, out of that broker process, but to instead its own process and have all the pipes go, various IPC channels connecting to there instead, was born. And I think this was more born in the era of Mojo IPC, where we had a more flexible IPC system that could help support that kind of transition, but still tons of work and quite a radical change to the flow of data and the way the system works. Previously, just to give a little aside, when a renderer is making a network request, the browser process, acting as a broker, needs to audit, is it okay for that guy to be requesting this thing? Think about all the kinds of rules that might be there, CSP, other kinds of things, and the security origin privileges associated with it, and what we want to allow a renderer to actually access. Simple stuff like, we support web UI like Chrome pages in the context of they load in a renderer process. That renderer process should be allowed to access other things from Chrome right? But a web page shouldn't be able to. We don't want the arbitrary web pages to be poking around and seeing what's available in a Chrome URL. So that's like a simple example of where we honor that isolation. And so the browser process, having the network stack, the original incantation of Chrome makes sense. It can apply these rules right there. Safe browsing was integrated there. Lots of different kinds of network filtering could be done there. Moving that to another process is a big change, because now browser's the one that has the smarts to do auditing, but the data and all the requests are going to this other process. So making that work meant a lot more plumbing and I think complexities ensued. But it's awesome to see it happen. I mentioned native client. So that was a precursor to WASM. That was a big investment by the Chrome team to find a way to bring native code to the web in a safe, secure manner. The initial take on it was, if you're running native code that came from the web on a system, that's scary. It could do anything, right? Well, no, let's restrict the process capabilities. But even with a restricted set of capabilities, you can't necessarily restrict everything on Windows or Mac or Linux. There's like always some limitation to the sandbox capabilities. And in many ways, the sandboxes that we've implemented are kind of like just an extra level of defense. If you think about it, the JavaScript engine is already a sandbox, right? It already limits the capabilities. The web rendering engine, all the different kinds of security checks throughout the code are various forms of sandboxing. And then finally, the process in the way we restrict its capabilities is that last defense. Well, running native code with only that last defense in place is not enough. So native client was designed to be not only to be native code that could be highly auditable, so that you can make sure that it's not allowed to jump to an address that it doesn't have code for, that it's not allowed to do things outside the set of things that it's allowed to do. So it has a lot of complexity as well in terms of how the process has to be set up, in terms of the memory layout, and various other details which maybe I'm happy to not remember. But it meant it needed its own process type. It couldn't just be, even though it integrated kind of like a plugin, it couldn't just be a plugin. It needed its own process type. And there had to be 64-bit variants and 32-bit variants, depending on the actual OS, your actual underlying hardware that you were running on, ARM versus Intel, all these differences. So yeah, we ended up with leveraging this process model extensively to enable these kinds of things. I think I mentioned the utility process. In Chrome, the utility process is this thing you reach for when you want to do something that's potentially, like maybe you're dealing with some untrusted input, like you want to decode an image, or you want to run something in a process, and you just want to make sure that if it's going to do anything, it just dies over there and doesn't take down the whole browser process. I think some extension install, manifest parsing, maybe various other kinds of things like that would happen in a utility process as like a safety measure. Generally speaking, parsing input from the web or even the web store or things like that, doing that parsing in the browser process is a scary thing because you're taking input from a third party, and if you're parsing it there, you might have a bug in your parser, and that could lead to the most trusted process having been compromised.
Yeah, that falls into the whole rule of two thing, right? Of untrusted data. We have a browser process. It's in C++. The thing that we decided to change is where it gets parsed. So
that's right.
That makes sense.
Yeah, so the process, sandbox processes get used as this primitive to give us that extra safety measure.
So the other process type I can think of that wasn't just covered there was extensions. Is there anything to say there?
Yeah, of course.
Of course.
In some ways, an extension process will show up that way in Chrome's Task Manager, but I believe it's usually just powered by an ordinary renderer, because so extensions have background pages or background event. In Manifest v2, it was background pages. Manifest v3, it's now like just event pages or service worker type construct, and those need a process to run in. So the extensions get to inject some code that runs in the renderer of the web page, usually in an isolated world, so it can see the same DOM if you've given the permission for the extension to read website data or to manipulate website data. It can do that by injecting a content script that will run in the same process as the web page that it's reading or modifying, but it will run in an isolated JavaScript context so that it's not seeing the same JavaScript variables and such, but it can still see the DOM. And that's meant to give a lot of capability, but also have a little bit of protection, because it's so easy to accidentally interfere with the same JavaScript variables and things like this. Okay, so extensions have that piece that injects a content script, but they also have usually they can have like this event service worker or background page that is the sort of their sort of central place for code to run. And so we do run that in a renderer process. And so, for example, if the extension that's injected into a page wants to get some capabilities, it would talk to its service worker who would then have the capability to ask for certain extension APIs to, maybe understand all the tabs that are in your system, depending on what permissions it was granted. And then finally, with extensions, you also have the extension button and a dropdown that can occur there, which a web page can be drawn there by the extension. And that's going to be hosted in a renderer process too. But that would be a web page that lives at like a Chrome extension : URL. And so you have these kind of like different pieces of the extension model where code from the extension can be running, and it can talk to, via some messaging channel, can talk to the other parts of itself that run in potentially likely different processes.
You mentioned service workers there, and those are kind of related to all this too. So can you tell us a bit more about those?
Yes. So, so backing up, in the context of extension, if we talk about like background page first, original idea with extensions was, okay, I'm injecting stuff into pages so I can modify things, but I also need like my home base. I need my context where I need like a place where my like persistent script is running, or where I can manage like my databases, and I have just like one place for that. And it's also a place where I can get elevated permissions to access other Chrome extension APIs. So that idea of like a background page that's like, that the extension can create, that's like ever present. So it's like a web page, but it's hidden, it's in the background, and content scripts that are injected into web pages can talk to it. So they can say, I'm on this page, give me some rules that I should apply to it or something, depending on the nature of that extension. Okay, so but background pages are unfortunately persistent, and they live for the whole life of the browser. And they use up memory, they use up resources, even if nothing else about the extension needs doing. Even if the extension's not loaded into any web pages, that background page is sitting there. And so we quickly realized this is not great. This is a waste of resources for the system. We should have some policy for how we should close that background page down and only need to create it when necessary. In the context of, I think, Chrome apps, which is a thing that's no longer a thing, we created this concept called event pages, which allowed for these background pages to be a little more transient, to come into being only as needed, which is a much more efficient approach. However, when it came time to bring that to extensions, at the same time, Service Worker had been created, which was a tool for web pages to be able to do background event processing. And so instead of the decision was to adopt that standards-based approach to how to do background processing. And so Service Worker is the construct that Manifest v3 allows extensions to use for that sort of background processing. Big difference between service workers are that they are not web pages, they're just JavaScript, but they can listen to different kinds of events. So just like a web worker, shared worker, service worker, they are without UI, they are without any HTML. They just have the ability but they have some functions that are given to them on the global scope that lets them talk to the outside world, to talk to the web page that created them. Or in the case of service worker, they actually have events they can receive to handle network requests on behalf of the page. That's the main use for them. One of the main uses for them in the context of the web. A web page would have a service worker register with the browser to say, "Hey, please contact my service worker if you are making a request for my origin." And that gives the service worker the opportunity to specify what content should be used to satisfy a URL. It could load that content out of a cache, and the service worker API includes APIs for managing caches and things like this. So all of that system that was built for, to kind of enable web pages to operate more robustly in the context of like poor network connectivity, or to get performance improvements for applications that are more single page applications that have like a basic fixed shell that should load out of cache, and then they make network requests to the server to get the data that populates some application UI. That model Service Worker was really designed for, but seemed like a very good fit for extensions, and it gets us out of the world of having these persistent extension background pages. So manifest v3 says if you want your content script to have an access to like privileged things, you go through an event system and a service worker. And the service worker will get spawned in a renderer process. What renderer process? You don't know. It's up to the system. Chrome will make a decision there based on, all of its usual rules around what other origins are in that process, thinking from a security isolation perspective, and and so on and so forth.
Cool. A lot of these process types have been added over time, as the need for them arises. Like, oh, we want to put network stuff in a separate process. So apart from adding more process types, what have been other big changes to the multi-process architecture and processes in Chrome in the many years since launch?
The biggest one by far is the per site isolation, the site isolation work that was done.
We'll talk about that more next.
Yeah, so I'll just say, Charlie Rice was intern on Chrome team back in the day when we were during the pre-release period of Chrome. And I remember the conversations where we're like, gee, wouldn't it be nice if instead of isolating based on per tab, it was isolating per origin? And I think he was doing research on that topic too. And he had all these ideas for this kind of a thing. And so it was really kind of very early on that we were having these conversations. But even very early on, it was like, this is going to be a big change. No longer is it the idea that, it's a big change to the rendering engine itself, like how frames could be served by different processes. So in order to isolate based on origin, you have to say a frame where an ad might live would actually have to be served by the process for that origin. And so now no longer is the whole frame tree just in one process. That's a big change. But built on top of the infrastructure we had, it was possible to imagine it, and it was quite a journey to get there. So that was probably the biggest change to the architecture. But like I mentioned before, actually, other big changes were definitely the introduction of the GPU process, definitely the introduction of Mojo IPC. Before Mojo IPC, the way things worked was messaging was much simpler, in some ways easier to understand, but also much more the case that there were these files that really needed to know about everything in their world, like the render process host and the render process, the render view host and the render view. The render frame host didn't exist then, but they came about because of site isolation, really. But the render view host became this thing that represented the web page. And render view host in the browser, render view in the renderer. And for any feature that required brokering out to the browser to get access to something, essentially the render view host had to be participants in that, because they had to be kind of routers for that traffic. That's not very scalable. You start adding lots of engineers building lots of different features that need lots of different capabilities, and these files start growing hairs and knowing about too many things, and it becomes really hard to manage. On top of that, you start to have like things where you say, gee, I really wish this system could live in a different process. I mentioned the networking process. Like all these events were coming through these different kinds of like crossroads of hell files. That's how I like to call them. And it's like in order to take a subset of that and move it to a different process, now you have to like redo all that plumbing. And so the amount of layers of repeating yourself for plumbing IPCs felt very out of control for maybe how much work you had to do to unlock a certain feature just seemed out of control. And so Mojo really was inspired by how to eliminate a lot of that, to have a system that's more endpoint to endpoint based, and all the flow of data would no longer be dependent on all of these kinds of routing classes that handled all this routing. And instead, you could just say, I have an endpoint over here. This one's privileged, this one's not. And if I want this to live over here, I can do that. I can just move it around freely. And all the routing's taken care of for me. And so that's that was a big change. And there's many artifacts in the code base that sort of reveal the old system, right? In many ways in which the system, the product is built still resembles that old system. The idea that, if you look at a render view host, there's an ID, a routing ID associated with that. Concept of routing IDs are not needed in Mojo anymore because the pipe itself, the Mojo pipe, is like an identifier, and in some sense. Of course, so much of our system is built up around the idea that tabs have these render view IDs and frames have render frame IDs and processes have process IDs. And so many systems deal with those integers that it's been unthinkable to not have those anymore. But in some sense, they aren't really needed. If we were to build things from scratch, from anew with the Mojo system, you wouldn't need it.
Do you think if you were to redesign the whole multi-process thing now, given how not just the internet is used, but also, the devices that are out there, I think you would probably want to have multiple processes for things. But do you think there would be significant changes to how the system overall is designed or put together if one were to start now?
Well, yeah, I mean, it's always a question of where you're starting from and what the constraints are that you're dealing with. We were dealing with taking WebKit, which we didn't really have a lot of ownership of. It was open source, but we also had limited bandwidth to go and fork it and manage that fork. And so to kind of try to create multi-process in the context of this big significant piece that we really can't change or do much about, definitely limited us. So when we had early ambitions and ideas, like I said with Charlie about site isolation, it wasn't going to be then that we could realize it. It needed to be in a place where we had ownership of Blink, and not just ownership, I mean capability to go and change it and to own the consequences of changing it, to be able to manage that. We needed that, and we needed a lot of other sort of pieces. So if I'm starting over, I also have to, it's sort of like, well, what am I starting from, right? But certainly I feel like a lot of lessons along the way inspired Mojo and the design there, and I feel like that's a system that sort of system would allow for, an architecture that I think would be better in many ways. And, I'm very biased because that's like something I worked on, but, and it was inspired by things I saw that weren't great about the way that we built Chrome originally. Although in many ways, the original setup with Chrome was born of pragmatism and minimalist in many ways, trying to achieve Chrome was very focused on being a product first, not a browser construction kit. And so the idea that it needed to morph into a lot of different things wasn't there in the beginning. In the beginning, it was like, you're just building a browser for Windows XP Service Pack 2. That's it. Nothing else. Okay, now Vista. You got to worry about Vista too. Sorry. But, just that's it. And then later on, you had Mac, you had Android, you had, Chrome OS, iOS, Chromecast, et cetera, and like suddenly your world is very complicated and the needs of this system is way more, and the value of malleability becomes higher. Look at the investment in views, et cetera, to allow cross-platform UI, and then Mojo to allow a much more flexible system under the hood. So it depends on your constraints in a lot of ways.
Yeah, that makes sense. Something you said about even now in the code base, you can see remnants or, suggestions of how obsessed maybe of like how things used to be. So one of the things that makes me think of is about the IO and UI threads, because I feel like people used to talk about those more, and now that's maybe changing a bit. So how come these are the only times we hear the term thread really in all of this? And what are the IO and UI threads? And can you just tell us a bit about?
Oh yeah, threading is a super fun topic. Now we have all these task runner concepts and systems for giving you like a task runner that's on an isolated thread or whatever. And systems like Mojo allow you to not really have to do a lot of plumbing to compensate for your choice of thread where you want something to run. You can just kind of indicate where it should go, and that happens. But okay, originally the design of the system was there was a UI thread, and that's where all the UI lives. So the HWinds, the window handles, and all the Win32 stuff will go there. Input painting come in there. Then there was, so early on, I like to tell this story because one of the very first versions of Chrome, we had just that UI thread sending data to a renderer processes, and the renderers would have their main thread where they ran JavaScript and everything. So there was just kind of these two threads and two different processes. That was kind of it. In the browser process, there might have been, the system was probably doing a lot of other stuff with its networking stack and DNS threads and such, but we weren't doing any, that wasn't us. That was probably libraries we were using. So we just had these two threads and two different processes and IPC channel. And so you send the input down to the renderer sends you a bitmap. Okay, Google Maps. Imagine Google Maps. And imagine you're on a single core, non-hyper-threaded laptop. And you take your mouse and you click on that map and you start dragging it around. And you expect to see the image tiles kind of moving around, right? But for some reason in Chrome on that device, nothing happens. You just move your mouse around and the image is stuck there. And you're like, what's going on? It works fine on this other laptop. Why not on this laptop? Turns out that on that device, in that setup, the input stream was coming in, and basically we were sending all this input, and the input events were taking priority in the Windows event pump over any painting, and so or reading from our IPC channels, and so. As a result, we were just sending input events to the renderer. It was doing work, generating new images. Those images were coming to the browser in backed up in some pipe and not really being serviced, not really making their way. And so we kind of came to the realization of several things. One is we need to throttle that input going to the renderer, but we also probably need to have some highly responsive I/O threads that could be dedicated to servicing the pipes, the channels, the IPC channels, both in the browser and the renderer, actually. And so what was born from that was the I/O thread. And the I/O thread was meant to be highly responsive thread for processing asynchronous I/O. That's really what its name should be. Highly responsive, non-blocking I/O thread. Because the name I/O thread subsequently confused lots of people who wanted to do blocking I/O on that thread, like read a file or something. And we had to put in some restrictions in the code to always let you know that this function is going to, like there's some runtime assertions if you try to use certain blocking I/O functions in base on the wrong threads. And alongside that, we invented something called the file thread. It said, this is the thread where you read files. This is the thread where you write files. Because we don't want you doing that on the UI thread, because the UI thread needs to be responsive to user input. So don't do blocking file I/O on the UI thread. Don't do it on the I/O thread either. Do it on the file thread.
And these threads are all running in the browser process.
In the browser process. The renderer got its own I/O thread too. So the renderer would have its main WebKit thread and its I/O thread. So it was sort of a symmetric system. You had IPC channel, which was wrapped with a class called IPC channel proxy. These things still exist in the code base. And channel proxy was a way to use an IPC channel from a different thread. But the IPC channel would be bound to the I/O thread. All of that, those things I just mentioned still exist, and Mojo was built on top of those channels. But the IPC channel provides that underlying pipe. So it's kind of like IPC channel is one-to-one with an OS pipe. Mojo has this concept of pipes, which are more like virtual pipes, and they're multiplexed over an OS pipe, one OS pipe.
Okay. Yeah, because I think, now you hear non-blocking I/O, but I feel like maybe it's just, what part of the code base you work in, but running things, making sure things run on the right thread seems to be less of a problem than it used to be.
Yes. I think there's a lot of reasons for that, a lot of maturity in the system, but also I think some of the primitives are set up nicely so that you can more easily have things running. In some ways, we used to have this concept of yeah, we very much had this, still in some ways still have this, but like the idea that there is a UI thread, that there's an IO thread, and that there is a file thread, and you pick which thread you're going to use. Now there's like a whole pool of blocking IO threads. And you don't specifically say I want the file thread. You say I have blocking IO I want to do, or give me I want to put it on a thread pool. The IO thread used to be like where, maybe still the case, that some systems would just live there only because maybe for latency reasons, like cookies is a good example. We knew that we wanted to be able to respond quickly to the renderer if it was querying a cookie database. So we want to be able to service that directly on the IO thread. And so there'd be a collection of these things that were maybe somewhat sensitive, but we wanted to like have them live and be on the IO thread. And so that idea of like some things live on the IO thread was born. But I think those things are few, and you really have to highly justify why you should be on that thread. And so most things don't need to be, just be on the UI thread, it's okay. Or structure your work so that the part that is expensive in blocking goes to a blocking queue.
So partly for these threads, sometimes you see checks like make sure check that this is running on a certain thread. But in general, is there a good way to find out what process a certain block of code runs on? Because some things right? If you go to, third-party Blink, whatever, you kind of know that that's going to run in a render process. But just looking at the code, like looking in code search, can you know where something is running?
Like prevention very early on to try to deal with this. So if you go to the content directory, it's a good one to look at. You'll see a browser directory, subdirectory, a renderer subdirectory, and a common subdirectory. And there's some other ones that have these familiar names. We use that structure all throughout the code base for different components. So if you go into components foo, you'd see browser, renderer, common, maybe a subset of those, depending on. And so the idea is if it's code that should only run in the renderer, it lives in the renderer directory. If it's code that should only run in the browser, it lives in the browser directory. If it's code that could run in either, it lives in the common directory. So you'll see like Mojam definitions in common directories, because Mojam is where you define the Mojo interface that's going to be used in both processes.
Oh, cool.
Yeah, this code separation was also kind of born out of this idea at one point in time that we might generate a totally different binary for browser and renderer. And, we used to have browser. I'm calling it that way because it didn't have an E at the end. So browser and capital R and then render or something like this. And these are the two processes, the two executables. And they could just compile whatever code they needed for their purpose. Like WebKit would be in the renderer, and browser would have not WebKit, it would have other things. And so these separate directories also helped because it was like, that's the code that's going to go into that process, literally. And fast forward, when Sandbox came along, and the team was like, nope, it's got to be the same executable for both browser and renderer. Should probably be called Chrome.exe instead. And then that idea kind of that they were separate executables and separate code kind of went away, and instead all the code for Chrome went into just this big DLL on Windows. And the amount of shared code between the exe and the DLL was very small, maybe a little bit from base and such. But this idea of like tagging the directory structure in such a way that makes it obvious, like what process this code belongs in, I think was a big help, and it was a good choice. Gives people like a little clarity of where they are and what they can use.
What about for non-browser renderer processes? What about like GPU network? How do you know that this is running on the network process versus this is how this part of this section of the code is interacting maybe with the network process?
Sometimes it can be a little bit of good luck. Sometimes it might not be as obvious. I don't think this sort of we did this structure that I described was used for plugins. So there's a plugins directory which may still be around in some fashion or might be mostly gone. I don't know if when the network process transition occurred, if this annotation was really maintained. I actually don't think it was, because I don't remember seeing network directories. But I could be wrong. There might be some of them. I'm not as familiar with the code for the networking process. But I think this convention has helped us a lot and would be valuable to use in more places. For GPU, there's a lot of symmetric code, probably code that runs in all processes, but still this convention probably would make sense. But yeah, I think that for some of those things, when you get like into the network world or you get into the GPU world, you're also kind of in a more focused world, a smaller world. And there's probably many other things you have to learn about that domain.
Yeah, the GPU stuff seems very, very difficult, and I certainly don't know how that works. Okay,
What's
so
going on there?
yes. So when it comes to process limits and performance and all that kind of thing, so we have process limits, but you can go over them. And can you tell us a bit about process limits, how they work, what happens when you reach the limit?
Yeah, so process limits, like they exist to just have like a reasonable number of processes allocated for some definition of reasonable. At least early on, that definition was based on how much RAM you had on your system. And as computers got more and more RAM, that definition needed to be adjusted. We assumed some overhead for individual processes, and it's probably wise to put some limits on how many we create. The allocation of those processes, it's best to, kind of viewed it as best to distribute the tabs across them as best as we can, and the origins across them now in the site isolation world, to give more isolation between different origins, to give more isolation between the different apps. But at some level, you run out and you need to now allocate across the ones that are already in use. There's some hard rules like around privileged content, like Chrome colon URLs. They should not mix with ordinary web pages. But it push comes to shove, we'll put a whole bunch of different origins content together into the same process. Just web pages, not ordinary web pages, not trusted content.
What happens if you just open a ton of tabs with a whole bunch of different pages open, and you're kind of like basically stress testing what Chrome can do? What happens in that case?
It creates a lot of processes, uses a lot of system resources, uses a lot of RAM. I think that Chrome, this has been, I'd say, a battle for Chrome across a lot of its lifetime, and more recently is how to manage these extreme cases. And increasingly, these extreme cases are not actually odd or unusual. People do a lot of browsing. People click on a lot of links. People create a lot of tabs. People don't really close their browsers. They just leave it running. And they come back to the next day and they continue where they left off, and they open more tabs and they do more surfing, and they just collect and collect and collect tabs. And maybe they create more windows, and because maybe they have some task that they're researching, and then they get interrupted and they come back to it later, but they start to accumulate these windows full of things that maybe they mean to come back to. And so that problem of just having lots and lots of stuff and lots of processes, well, Chrome under the hood is like, I'll do my best. You wanted me to do all this stuff, I'm going to do it. Let's see what I can do. And on a system like Windows or Mac, where there's a lot of RAM, maybe Chrome's thinking, okay, you wanted me to use the RAM, I'm going to use the RAM. You wanted all those tabs, and then even on those systems where maybe you're running out of RAM, but there's virtual memory, there's disk space. All right, let's use it. Let's go. And so I think it's really quite a challenge, actually. The original idea of Chrome was, make it possible for web pages to take advantage of the resources of your computer. Allow web pages to be more capable because of it, and not be, the old world, but prior to Chrome, was single-threaded browser, all web pages on the same thread. Like, you could have a dual-core machine, it wouldn't matter. It wouldn't make your browser any faster. But now with Chrome, no problem. You got dual-core, got 8 cores, whatever you got. We can have all of those things saturated with work and allow you to multitask on the web and do lots of amazing things. But I think it's still a resource management challenge for the browser. Because, on one hand, you want to give that capability, but on the other hand, you also don't want to, how much power should you be using? What if the laptop's not plugged into battery, to the wall? What if it's just running on battery? What is the right resource utilization for Chrome. I don't think that's a solved problem at all. There's various systems in place to throttle the resource utilization of background tabs. Timers for a long time now have been throttled, but throttling other things. I know there was a lot of research done into like freezing tabs, so literally suspending them and not letting them do any work. But with that comes challenges of like, what do you do with all the IPCs that are inbound to those processes? They're backing up on pipes, and that's not great. If you unfreeze them, now there's like a blast of IPCs coming in that they suddenly have to service. That doesn't seem great. Do you drop those IPCs on the floor? Probably not. Now the process would be in some weird state, and you might as well have to just kill it, which of course is the case on dev systems like Chrome OS and Android. They do have to just kill the processes because of the limits of those devices. I've been a proponent of just being aggressive about killing processes on desktop in general. I think there's some balance there that's right. It's probably not right to keep all the tabs open, all the processes open. We should be, I think, judicious about what we keep open and keeping the workload reasonable instead of making it like I will rise to the challenge of dealing with thousands of tabs, or thousands of web pages across 100 processes, even if maybe it's somehow possible through heroic effort to make Chrome capable of doing such a thing in an efficient manner. But does it mean we should? Who needs 1,000 tabs all running around doing work at once? You don't. You really don't. Nobody does.
So this is kind of the basis of the goal for Arc, right? Which is, I think, like it closes your tabs overnight or something, and Arc is what you work on now, and is a Chromium-based browser. So for embedders of Chromium, let's say the browser kind, how much control do you have over how processes are used, allocated? If you embed content, like, are you able to just say, oh, I don't want a network process, I will just put this all in the browser process? Can you do that?
You can do anything you want. It's just code. No, but as a browser embedder, as a Chromium embedder, you're shipping Chromium. So Arc browser ships a copy of Chromium, and Arc browser includes changes to Chromium as needed to make it work. Of course, that's possible. Of course, could change a lot of stuff and make a big headache to manage it all, right? So there's some natural limits. You don't want to change too many things, or else you won't be able to really manage it going forward. You want to take updates from the main line, incorporate improvements, but you also want to preserve some differences that you've made. Well, how do you do that? And so change management is a challenge. So there's a natural limit to how much you want to alter the base functionality. Instead, it's anyways, a product like Arc is not so much differentiating on the basis of Chromium code or content layer. It's not really its purpose or goal. Its purpose is to differentiate at the UI layer, and with things like what you mentioned and other things as well. And so, of course, if one were to go down the path of like, could we optimize process model better, that would be in the realm of things that would be great to contribute to Chromium so that it could be part of the mainline and therefore not be something that you have to maintain yourself. That's how I would approach it as a Chromium embedder.
Okay, that makes sense. Yeah, if it's in Chromium, you don't have to worry about the updates, and you just get.
Turns out there's an army of engineers who would make sure it's never broken. You just have to write some tests.
Wow.
Data those tests.
With non-browser embedders of Chromium, like say Electron, I don't know how familiar you are with that, but they presumably would have different needs for out of how it all Chromium works, basically. I don't know if you know what they're doing with any processing.
I mean, I've used VS Code. That's a famous example of a Chromium embedder that you might not realize is using Chromium or built on top of it. That one might not realize that. But if you open up Task Manager, you look at VS Code, you'll see all the glorious processes under there. And so, have they or Electron or any of these, have they altered things there? Maybe. I mean, there's some configuration one might do. If you're building an application that's very single purpose, like VS Code or Slack, or what are some other good examples? There's quite a few that are maybe that are built on top of Chromium. They're more single purpose towards a single app, right? Of course, VS Code's pretty sprawling with all the things you can do in it, but at the same time, it could be the case that they don't have the same security concerns. They don't have the same idea of like hosting content from so many different sources. So maybe they would tune the process model a little differently. Maybe they would decide, I don't really need as many processes because, you know, I'm managing things in a different way. It's not a browser.
Mm-hmm. Yeah, you're not handling all of the untrusted JavaScript of the web that you have to be prepared.
And I'm not so worried about like this part of my application dying and then wanting to keep the rest of it still running or something, because my app would still be considered a bug because part of my app died. And so some of the reasons for multi-process architecture might be a little different.
Right. And more just for fun, having worked on now an embedder of Chromium, how has that experience been in terms of, you know, decisions that were made when you were putting together the multi-process architecture? Are there things where you were like, oh no, past me, if you'd done this differently, this would be easier now?
I would say I'm very thankful for Mojo IPC. It's made it very easy to, one thing that I've found is that it's possible to do a lot of amazing things on top of Chromium without actually modifying Chromium.
Okay.
And the content API and Mojo IPC makes a lot of that really possible. So it's a very flexible system. There's a lot of really great hooks that let you interact with the system from, you know, all the way from extending the renderer to extending the browser, and to be able to build stuff and layer it on top of a stable system is amazing. You know, when I was working on building an Android browser, I built a tracking prevention ad blocking system for Android and was able to do it without modifying Chromium. I thought that was amazing.
How are you using Mojo? Because Mojo's typically going between the processes. So if you're not really changing how the processes work, what do you use Mojo
well,
for?
In that case, it was used to communicate a rule set down to the renderer. And then at the renderer level, I would inject a style sheet to do content blocking, or to apply a network filtering at the Blink layer. So the combination of Blink public APIs and content public APIs, there are actually enough hooks to be able to filter network requests and insert style sheets that would apply display none to a set of DOM elements. But to do that efficiently, it was necessary to bundle up those rules into like a blob of memory that you would just send down to the renderer process, to all renderer process, so it would have it available to them so they could just directly inspect like a big hash map of rules. And so being able to, like I said before, when the IPC system is just like when it's decoupled like that with Mojo, it makes it possible to kind of graft on these systems that they interact with APIs over here, and that endpoint talks to some endpoint over here, which can, in the browser process, which can have like I said, like a rules data that it might want to send over and that kind of thing. And so being able to build those kinds of systems, and I think if you look at just how a lot of features in Chrome are built, they're built very similarly too. They build on top of the content API that provides the various hooks. They build on top of Blink API. Sometimes a feature needs to live in the renderer and the browser process. Like autofill was always the classic example of this early on in Chrome, or password manager. These are systems that need to crawl the DOM. They need to poke at the DOM. They need to like understand what's there. They need to be able to like insert content or put overlays in, or they need to be able to talk to the browser where the actual database is, all that kind of stuff. And looking at different load events and various things to know the life cycle of the page. So yeah, I'd say I'm thankful for a lot of these design choices along the way, because I think it's led to Chromium being so useful to so many people in so many different ways. Obviously, it empowered building a really great browser and a really great product, but it also has empowered a lot of follow-on innovation, and I think that's pretty cool.
It is pretty cool. So Chrome was released in 2008. It is now 2023. So as math tells, it's been 15 years. We like numbers that end in 5 and 0. So I don't know, it's very cool. I remember when Chrome came out, and I don't know, do you have any?
For me, it's more like 17 years because we started
Right.
in 2006.
Right. So do you have any general reflections on like all of the stuff that's changed in that time?
It's wild, I have a higher density of memories from the early days too. It's amazing. I guess that's how memories work. When everything's new and changing so much. But yeah, no, I'm very thankful for the journey and very thankful to have been part of it. And it's a lot of fun to work on. I mean, prior to Chrome, when I was working on Firefox, I did a little exploration on adding like a multi-process thing to Firefox, which I thought, I was learning about how to do IPC, and I was learning, but I was doing it for what purpose back then? I think I was just toying around with like DCOM. I don't know if anybody knows what COM is, but Microsoft's component object model that was like all the rage back then, and it allowed for like integrating like different languages together. WinRT is all built on top of this stuff now. But anyways, Mozilla had its own version of COM called XPCOM. And wouldn't it be cool if you could have like a component that, so you could have components back then that were like built in JavaScript and you could talk to them from C++, or they were built in C++ more commonly and you talk to them from JavaScript. But wouldn't it be cool if like one endpoint could be in another process? So that was something I was playing around with in 2004 when I was still working on Firefox. And then when Chrome opportunity came along, maybe that was 2005, I don't know. But when the Chrome opportunity came along, I was like, all right, let's do it. The IPC channel was basically those ideas, but kind of more polished slightly.
Okay. Yeah, very cool. I mean, when I first started working on Chrome stuff, someone on my team said, anytime you change something in base, that pretty much is going to get run anytime the internet gets run, which I thought was super crazy for like just some, random software engineer like me to be able to do, right? But
and now it's even more than that if you think about code and
yeah, it's all the stuff. So do you ever just think about it and you're just like, oh my God, wow.
Yeah, it's pretty amazing.
So crazy.
It is one of the special things about working on Chromium is that, yes, you can have such an amazing impact with the work that you do there.
Mm-hmm. Have there been any cases, these are just now unrelated miscellaneous questions, but in terms of, surprising usages of Chromium, be it like maybe the like base or like the net stack or something, have there been any cases where you were really surprised of like, oh, this is being used here?
Well, for sure, the first time I heard about Electron, I was like, oh, this is not a good idea. House of cards, it just seems like it's such a complicated system to build your app on top of, right? But at the same time, I totally get it and appreciate it, and I understand why people would reach for it. There's so much good sauce there, so much good stuff, and there is a lot of really good infrastructure there to build on. Early on, I kind of imagined more that like things like Skia and V8 and some of the other libraries would be the thing that people would make lots of extra use out of, right? So I didn't quite imagine people taking the browser as a framework like this. And we absolutely didn't build it with that purpose. Like pretty much every choice along the way was highly motivated by making Chrome team's life better. Like Content API was, when we came to the realization we needed it, it was like we desperately need it. Like the complexity of Chrome was getting unwieldy. We needed to cleave part of it and say, that is this part. We needed to somehow draw a line in the sand and say, this is the set of concerns over here. And so, the idea that all of this could be used for other purposes is cool, but it was never really in the initial cards. And, I came from working on Mozilla, which was in many ways browser construction kit first, product second. So Chrome was very much like, let's go the other extreme, product first, maybe a platform later. And to see it be this platform now is pretty cool, but like it's pretty far from where we started.
Yeah, kind of. I watched some of the earlier talks you gave about the multi-process architecture, and content, not Chrome, came up a bunch, and
Yes.
this is things I guess like Electron are the result of that, right? Where it's
Yeah, it's pretty wild. Yeah, I mean, just like so Mozilla built this very elaborate system called Zool or XUL, which was a like XML language for doing UI, and it's very interesting, intellectually interesting. Like maybe different than XAML. XAML's way better, probably in many ways, but Zool was kind of like XHTML minus minus with a bunch of stuff added on for like UI things. And then it had this thing called XBL, which is a bindings language that you could do custom bindings. And so, anyways, then you build your application in JavaScript. Firefox, Mozilla, it was all built this way. So it was like a web page hosting a web page. The outer web page was like this XML DOM. The product engineers working on that, in order to get like some modern Windows sort of thing come through, they had to basically go through the rendering engine team to get them to do something. And so it really greatly limited the ability for product team to actually build product. And there were so many sacred cows around the shape of Gecko and how that structure was, that while this cross-platform toolkit seemed glorious at first, it ended up being handcuffs for product engineering, I think. So yeah, Chrome started out with like Win32 native UI for browser UI. You have all the choices you want to make, browser front-end engineers. You also have to build a lot of code, but no cross-platform toolkits, that views came later.
right. Well, this is great. Thank you very much. Normally we do a shout out section at the end. Do you have anything? Normally it's like a Slack channel or something like the Mojo Slack channel. I think in this case it's maybe, I don't know if there is a specific thing, but is there anything?
Shout out to all the team and the engineers making everything great.
All right.
Yeah.
Cool. Awesome. Well, thank you very much for chatting with us. That was super cool. Lots of really interesting background and like good information. So thank you very much.
Yeah, pleasure. Thank you so much for having me.
Talk about threads. So IO UI thread. Um,
Yeah, I get credit for the confusingly named IO thread.
okay. All right. We can cover that. That's cool. Why is it called? Yeah. Why is it called IO thread when it doesn't do IO?